hopefully this idea of line search makes some sense. And I shuffled to the wrong page anyways. Okay. So here's the cool thing. In general, line search is a difficult problem. In fact, on your problem set, if you do the extra credit, you'll argue that sometimes it's good enough to not solve line search completely, you just kind of have something that is better than where you started. But for this particular choice of f of x that I've written here, I can do line search in closed form. I can find the position of alpha that minimizes this f completely, right? Which obviously is what I'd like to choose for line search. Yeah? So let's do that calculation. It's actually not so bad. Pacing around like a madman. Okay. Right. By the way, as you guys have seen, I am horrible at bookkeeping and signs and indices and things. Conjugate gradient is going to be like maximum entropy for me, so the second that you see something that looks suspicious, you should stop me, because it's likely a mistake. Cool? Well, I'm looking at you, man. You usually keep counting. Okay, so, right. So again, we've defined this function g of alpha to be f of x plus alpha times the search direction. For now, I'm not going to assume that d is the gradient of anything. It's just some search direction. I don't even care. That's going to be important because I'm going to reuse this formula when we talk about conjugate gradients. Yeah? But anyway, so let's write this function out. Well, he's nothing more than 1/2 times x plus alpha times the search direction, all that transpose times a times x plus alpha times search direction, minus b transpose x plus alpha times search direction yet again, plus c. You guys see what I did there? I just plugged in this guy for s. Okay. So now we get the pleasure of doing huge amounts of algebra, and in particular we need to expand this yucky triple product here. So let's do that. Secretly, it's really nothing more than FOIL from algebra. Right? So you're going to get an x transpose AX plus, now the nice thing is that A is symmetric, so in fact I know that the middle term kind of looks like 2 times alpha x transpose times A times D. Hopefully I did that right. Yep. Plus, and then these two terms, right? Alpha squared D transpose A. Yeah? Minus all the other stuff. So in fact, let's expand this guy out. So we're just going to make this like the maximum yucky optimization problem, right? So this is minus B transpose X minus alpha B transpose D plus C. Cool? So I've just expanded this thing as wide as it'll go. Now here's the thing. What is my unknown here? Okay, the question you got to keep asking during lecture. My unknown is alpha. It's one number. All these other things, A, B, C, D, I think that's all. Yeah, 1/2 I suppose, are all known. Yeah? So this function secretly is just a quadratic. Right? I have an alpha squared, an alpha, and then a bunch of constants. Right? Well, that's great. In fact, let's write it in this form. Right? So what is he going to be? He's 1/2 alpha squared times D transpose AD plus alpha, and then we'll just factor out everything with an alpha next to it. Transpose AD minus B transpose D plus, and then everything else is just some constant. Yeah? So all I did was refactor this thing. And anything that doesn't have an alpha next to it, for example, this C and this B transpose X, just goes into this. Cool. Well, okay, so this is a function of one variable, and we're trying to minimize it. So in our hierarchy of problems, this is about as easy as it gets. Yeah? And in particular, we get that G, can I squeeze it in here? I think I can. That G prime of alpha is equal to, well, the 1/2 and 2 cancel, so you get alpha times D transpose AD plus X transpose AD minus B transpose D. Cool? Alright. So look what I just did. We now know, right, we want to minimize this thing with respect to alpha, so this thing equals 0. Yeah, and once I fly back to the other side of the room again, we find that we have a formula for alpha. Yeah? In particular, we know that alpha equals d transpose times b minus ax. That's a d. Sure. Divided by b transpose a d. Super simple formula. By the way, this thing is just like a dot product. Right? I wrote it in matrix form. Nothing complicated. Yeah? So if I want to do line search, and I'm in particular working with this choice of f, it's not so bad. I just plug into this formula. I don't have to do Wolf conditions. I don't have to run bisection or whatever the heck, golden something or other. All I have to do is just plug in this formula, and I know, if I parenthesize properly, that in fact, the alpha minimizes this f completely in a search direction. This is looking promising. Yeah? So we're going to box this formula because it's important. Now in particular, let's say that I am implementing gradient descent on f, right? But what do I notice about the second term here? B minus ax is exactly the search direction d. You see that? So for gradient descent, in fact, this is just the dot product d transpose d divided by d transpose ad in even nicer form. Yeah? By the way, when I take the gradient of a function, right, I really expect, when I move, I expect to move in the minus gradient direction, right, which in particular means that alpha should be greater than or equal to 0. And we can check that that's true for our formula here, right, because this is just the norm of d squared, and this is a positive number because a is positive down. Yeah? Cool. By the way, obviously if ax equals b, then you divide by 0, but you shouldn't be iterating more if ax equals b, so we're not worried about it. Okay. Yeah, so anyway, we have this nice formula for alpha. This minimizes your line search in closed form. Yeah? No matrix inversion needed, just dot products. Okay? So I'm going to be like Billy Mays today. This is a super, super convenient, nice, easy to use formula, and one that you should like repeat to yourself 10 times when you wake up in the morning, because it is so interesting and important. So anyway, if I want to implement gradient descent on f for solving ax equals b, it's 3 lines of code. At least in MATLAB, plus matrix multiply, all that kind of stuff. Right? Well, what is it? Well, the first thing I'm going to do is compute the search direction. That's just b minus ax. The second thing I do is compute how far along that search direction I should go. That's this number alpha. The third thing I do is actually move. Then I'm done. Then, well, I'm not done. Then I repeat back and do it over and over again. And eventually, this thing will reach the minimum of f, right? That's what gradient descent is designed to do. Yeah? So, how many lines of code do you think the typical implementation of Gaussian elimination with double pivoting and everything else is? It's like pretty big and pretty easy to get wrong. This guy gives you the same answer in 3 lines of code. So already we're pretty encouraged. But what haven't I told you yet? Well, we know that f decreases in each iteration of this algorithm, right? We kind of guarantee that by our choice of alpha, right? But I haven't told you how long it takes. In particular, right? What if so a very typical thing to do would be to plot a function where we're going to say that this x-axis is k, right? Like which iteration you're on, and the y-axis is, for example, the residual b minus ax. Yeah. Now, what I really want is for the function to look like that, right? That says that in some amount of time I reach the minimum, I'm happy, and so on. But in fact, if I implement this algorithm, what I'm going to find is that it looks more like this. And it goes on. You know that eventually it's going to get really close to 0, but I haven't told you how long it could take. So so in fact, in your lecture notes, as a math guy, I have to actually prove to you that this can take a really bad amount of time, but I decided to remove it from lecture because it's sort of secondary. And instead just quote the bound that I computed these notes. So you can see it's a little bit hairy. But what's important here is that the ratio, so x star is the minimum we're trying to find, right? But it's a convex function, so we know there's only one minimum. And you could compute this ratio, which is f of the current iteration minus f of x star divided by f of the last iteration minus x star, right? So this is just like how much closer am I to the minimum than I was before. And you can bound it above by 1 minus 1 over the condition number of A. Right? So first of all, do we want this number to be big or small? David, do we want this number to be big or small?
Which number, the whole thing or condition
The thing on the left.
On the left, small.
Small, right? Because what that says is like, okay, in my current iteration, my distance to x star is really small. My last iteration is, well, bigger than it was. Yeah? So to do a sanity check here, right? Well, a good condition number is one that's close to 1, right? So as my condition number goes to 1, this number goes to 0, which is good. So for a well-conditioned matrix, gradient descent works pretty well. Now, what happens as my condition number gets worse and worse and worse? Well, the condition number gets bigger, right? Poorly conditioned matrices are ones that have large condition numbers. In particular, this ratio goes close to 1, right? And if this ratio were to equal 1, for instance, then I don't even know that gradient descent converges at all. Right? This is the ratio of iterates from each step to each step. So, what do we know so far? We have a super easy method to solve AX equals B. In fact, if you're lazy and you have like just a typical matrix that's nicely conditioned, like comes from an elliptic PDE, which we'll discuss in a little while, then go ahead and use gradient descent. In fact, do it without a preconditioner, and chances are you'll get to the minimum of this energy in a reasonable amount of time. Yeah? And if you're not in a hurry, that's fine. It's very easy to implement. But as you get poorer, like worse and worse conditioned systems, this strategy becomes basically not a good idea. By the way, from a theoretical perspective, this is good. You know your condition number is always big, greater than or equal to 1. Yeah? And in particular, that shows you that this algorithm is guaranteed to converge. Right? Linearly. Okay. I might finish early. That's good. We'll get to jump on next lecture. So, right. So there are a couple of weird drawbacks of the gradient descent algorithm on this f of x that I wrote down. Right? The first is we already know how to solve ax equals b in n cubed time. Right? Like in a finite number of sets, I can give you the honest-to-goodness solution x to ax equals b without any error other than like IEEE precision kind of stuff. Yeah? Just by running Gaussian notation. So if I take more than n iterations of gradient descent, then this is actually worse than Gaussian elimination. Do you see that? Because each iteration of this algorithm is going to require multiplication by this matrix A, which could take n squared time. Yeah, so if I take n iterations, that's n cubed time, and I might as well have done Gaussian elimination. Well, that's not so great, right? Why, I mean, we have a method, somehow we don't expect any method to do worse than Gaussian elimination, because that's sort of like the heaviest hammer that we have, right? He can solve any linear thing if you give him enough time, in n cubed time. And when your matrix is poorly conditioned, you can have a lot of repeated work. Now, Shuchuk does a good job of plotting this, and I should have included one of his plots in my lecture on my slides, but I didn't, so I will draw it for you because it's very easy to draw. So, a typical thing to do would be to think of your vector x as being in R2, so it's on the plane, and to draw level sets of this function f. You all know what level sets are? Yeah, just like places where f of x equals 1, places where f of x equals 2, and so on. So you can think of this as like a projection onto the whiteboard. Yeah? So let's say that here's the plane. Right? Now when f of x is nicely conditioned, the level sets of f of x look like nice circles. Right? So let's say that I'm standing at a point here, and I take the search direction minus the gradient, but he kind of points downhill, right? Incidentally perpendicular to the level sets. And you can see that when I do my nice closed form line search, right, it's going to search all along this line, it's going to get pretty darn close to that minimum. Right? And so somehow when you have a well-conditioned matrix, your level sets are all these nice circles, right? And then your gradient pretty nicely approximates the direction to the actual minimum of this function, and life is good. In fact, you can show that if your matrix has all the same eigenvalues, then gradient descent converges in one step. which you can kind of see from this picture, right? It looks like it's going to aim right to the center of the target. Now, is it okay if I erase f of x, or do we want to keep it here? We should keep it. Yeah, so let's say that our function is poorly conditioned. Well, now if you think about it, level sets f of x are going to look like ellipses that are very skinny, right? So let's say here's the optimum, and you're going to get like a little ellipse, and a wider ellipse, and a wider ellipse, and so on, right? Because what does a poor condition number mean? Remember, that means that you have the difference between the biggest and the smallest singular value is very large, right? So in one direction you're scaling a lot, in one direction you're not scaling very much. And that's why you get this kind of ellipse structure. Just be careful with the word elliptic. Okay, so here are my level sets. And let's say that I'm standing at this point, right? Now, the line search I'd like to do would point me right at the minimum, right? If somebody could give me that direction, then life would be good. But in fact, what is the gradient of this function? Well, locally, the best way to minimize f, right, you move perpendicular to level sets, is actually to move this way, right? So great, so now I minimize in this direction, I get over here somewhere, yeah? What's going to be my next minimum? One's going to point a little bit down this way, and so on. So when you run gradient descent on a poorly conditioned matrix, what happens is you end up zigzagging toward the optimal point. You can take a very long time. Somehow the reason for this is that you're doing repeated work. You're optimizing a lot in this perpendicular direction because that's where your gradients point. But that's not the direction you should be moving to get the most sort of bang for your buck for a step that's larger than just, infinitesimally looking at your toes. Yeah? So, sort of philosophically, we feel like we should be able to do better, right? The Gaussian elimination already tells us that we can solve this problem in n cubed time. So if we do any worse than that, then this is a worthless method. And plus, some of the iterates of gradient descent on poorly conditioned things do something stupid, right? And somehow you should be able to look at the fact that they're wiggling around and realize that this is a bad idea and fix it. And that's more or less what the conjugate gradients method does. So, now we're going to make an observation. So I looked at a bunch of different proofs of the conjugate gradient method. And I found one I really like, which is, this is in Golub and Bedlone. Although I simplified it because that book is horrifying. And the observation here is that our function f actually takes a different form, which is really interesting. In fact, it turns out this proof exists every which way for conjugate gradient. Heath does not provide a proof of conjugate gradients, it just states it in a box and moves on. So I wouldn't look very closely at that chapter. I put a little question mark on the course book here. Right, because this is, you're going to see in a second, that this is not an algorithm, you just state in the box and move on. Okay. So, this is our form for f of x. And in fact, actually, it's okay if I erase the gradient. Hopefully we're kind of good at that calculation. Yeah? So, let's say that x star is the position of the minimum of f. Remember that means that ax star equals b? Yeah? Hopefully we're cool with that now. Well, one thing I could do would be to kind of subtract x star and then add it back on again and see what happens to f. In particular, let's say this thing is equal to 1/2 x minus x star transpose a x minus x star. Okay, well it's not really, so I have to subtract any terms that I just added here. Yeah? In particular, that means that I have to add a x transpose a x star and, sorry, minus 1 x star transpose a x star minus b transpose x plus c. You see what I did there? So I added these minus x stars, right, and then I foiled them and subtracted out the extra terms down here. Right, algebraically I can certainly do this. This is just, making it more complicated than it was before. Why wouldn't we want to do that? Okay. But we can make a couple observations about what happens here. So first of all, maybe I'll get a different color so that it doesn't turn into a big mess. What is ax star? Remember, this is x star is the optimum of f. B. Ax star is b. Thanks, Dave. Here he is again. Cool? So, in fact, well, now what? Well, we have a minus 1/2, so this is, right. So we have x transpose b with a plus next to it. We have b transpose x with a minus next to it. So these things cancel. Cool? Yeah, this is surprising. So, what does this energy function look like in the end? Well, is this thing a function of x? And I know this is a weird way to write the form of f, but x star is actually a constant here. This is the solution to ax equals b, right? So in fact, this thing and this thing are both just constants. So what is the form of my function f, really? This is super cool. F is equal to 1/2 x minus x star a x minus x star plus a bunch of constants. Right? So if God had given me the solution of my optimization ahead of time, then in fact, my function f takes this really weird form where all it's doing is it's measuring the distance to x star explicitly. It's with this annoying a stuck in between. Yeah? And in fact, this is where I differ a little bit from other people's notes on this matter. Since in 205A we have exhausted to death the Cholesky factorization, let's use it. Right? So we know that A is symmetric and positive definite, so even if it takes a million years to compute the Cholesky factorization, we proved it exists at least. Yeah? So in particular, I can write A equals, actually this is review. Somebody knew, what is the Cholesky factorization of A? Yeah, LL transpose. Thanks, Mindy. Okay. Yeah? If you don't remember that, you should look back at your notes. Okay? So, if you recall that, yet again, that homework problem we had, remember we talked about inner products and Mahalanobis metrics and so on. Right? We did exactly this substitution, where we took A equals LL transpose. And what did we get? We got that, we'll switch back to green. We got that this whole function is equal to a norm. In fact, equal to 1/2 the norm of L transpose x minus x star squared plus constant. I don't know what that symbol is. Okay, that's the 2 norm. Yeah. Cool. This is really odd. You see what happened here? I wrote down a quadratic form that I want to minimize for this point we're trying to find x, but in fact, secretly the quadratic form is really just x minus the optimal point. It's just the distance from x to the optimal point. That's all it is. Just with this weird matrix L transpose, but L transpose is invertible, so somehow this whole thing is super simple. Right? So in fact, what we're going to do is a little bit of a trick. We're going to do a change of coordinates, we do a little bit of math, and then we're going to change back. Okay. In particular, we're going to do the substitution that I've written on the slides here. The y is equal to L, so we're going to distribute this product. I'm going to say this thing is equal to y, right? So y will define to be, L transpose x. And then for this guy, we're going to say y star, well, he's just going to be L transpose x star. Remember? I'm trying to make my problem as easy as possible. Now, by the way, is this going to lead, what do you think? Is this going to give me a proof or is this going to give me an algorithm? Well, initially this is going to give me a proof because I don't want to actually compute the Cholesky factorization of A. Yeah? So this is just a convenience for us to think about what's going on here. Yeah? But if we do that, then we can define a function that we're really moving around and we'll call him f bar of y, which is just the norm, I guess 1/2 to be consistent, of y minus y star. Yeah? World's easiest function to minimize. Yeah? In fact, if I run gradient descent on this one, it should converge in one step to y star, because the gradient obviously points right at where you're going. Yeah? So, in that sense, maybe you should be thinking in your head, like, okay, well, Justin, you've gone too far You finally, this does it, this is stupid, this function is ridiculously easy to optimize, and you're right, it is. But only if I knew y star. Right? So let's say I could play a game where I can do line searches on f, but I can't actually just query f to know what its form is. Because that's sort of similar to what we're doing in gradient descent. Right? We can do line searches, we can search around our feet, we can walk down the hill, but we can't somehow step back and look at the whole valley and then just jump to the minimum. Yeah? Well, with that philosophy in mind, I provide you with a proposition. By the way, this is of my own design, so chances are it's wrong, but my guess is that it's not wrong. In particular, yeah, now everybody starts getting. So, let's say that I choose n orthogonal vectors, so just an orthogonal basis for Rn. Yeah? So we're going to call those W's. Then, what I claim is that if I do n line searches on f bar, right, this stupid function I've written here, if I do n line searches, the first line search being along W1, the second one being along W2, the third one being along W3, and so on, that when I do these n line search, after the nth line search, I am guaranteed to be the minimum of f bar. F bar. Yeah? This is sort of a reasonable proposition. I can draw you a picture of what's going on. So, right. In particular, what is this thing saying? Well, it's sort of saying, so let's say that here's this guy, and we'll say that this is y star. Right, so our target is right in the middle. Yeah? So I'm saying if I'm at some point here, that I choose two orthogonal directions. For example, maybe the first direction I move in is this one, and then the second one I move in is that one. Yeah, you can see that I zipped right into the minimum of this function. Yeah? Now, can we prove this proposition a little bit more vigorously? Absolutely. So in fact, let's define a matrix Q to have columns that are the W's, right? So this would be like W1, Wn, right? Q is an orthogonal matrix. Okay? Now, what do we know about orthogonal matrices is that they preserve the lengths of things, yeah? As do their transposes. So in particular, I can say that f bar of y, right, since orthogonal things preserve lengths, an alternative form for him is q transpose y minus q transpose y star. Yeah? He preserves the length. Now what's going on here? Well, so this is just computing the dot product of y with each of the search directions w. Right? So in fact, let's do one additional substitution. We're going to call this vector, not w, because we already have w. We'll call him z, and this vector z star. Yeah? And let's say that I optimized, I don't know, f twiddle, what's another name? This is when I should have reviewed my course notes before lecture. Whatever. We'll call him h. h of z is equal to what? Well, now it's going to be z minus z twiddle, or z star. They're just like the y's. But now, what are our search directions? Well, if you think about it, your search directions are the standard basis vectors, e1, e2, and so on. Right? All I did was I rotated my coordinates so that w1 is like the x-axis, the w2 is the y-axis, and so on. And from here, I think it's pretty easy to check that if I start with the line search, what's going to happen, right? So initially, right, z is equal to just some vector z1, z2 to zn. I don't think we need to check this explicitly. What do you think will happen after the first line search? Well, the first line search is just along the x-axis, right? The first coordinate. In fact, it's going to replace z1 with z1 star. Yeah? What's the second line search going to do? It's going to replace z2 with z2 star. And after n line searches, oops, I already put a star there. It's going to replace the nth guy with zn star. Right? So basically, in other words, right, if I have these two coordinate axes, then obviously the easiest way to find the origin from this point, if I can only move vertically and horizontally, is to go up like that, and then over. I think this is a reasonable proposition. So in fact, that proves, so now if we go back, we say, okay, well all I did to go from W to Z was rotate, so obviously if this is true, then this claim is also true in our rotated coordinate system, and that finishes our proof. Yeah? At least a sketch. Cool. So this is a proposition, or a theorem, or whatever you want to call it. It's not an algorithm yet. Yeah? But this gives us some idea of what we can do. So now, remember we made this funny change of coordinates, right? We introduced L. Shoot, I erased it. We introduced these y's by multiplying x and x star by L transpose. Well, now I've got to undo that, right? But thankfully, if you think about it, I'm going to make a little bit of an intuitive argument here, which is what I'm going to have to do a lot for conjugate gradients, because the proofs are just, there are a lot of them. But do linear maps affect lines? So if I draw a line in the plane, now I take every point in the plane and I multiply it by some matrix, I claim that the thing that comes out is still a straight line. I think this is pretty clear, right? Because all that linear objects can do is rotate and scale, right? In fact, we know this from the SVD. You know? See, it's synthesis. I'm told that's what I have to do. Okay. So in other words, remember we had this function f bar, where what we did is replace the x's with L transpose x? I claim that if I do a line search of f bar along a direction w, that's the same thing as line searching our original function f along the line that you obtain by undoing that transformation that I did to go from f to f bar. Does this make sense? So basically, what I'm claiming is that we sort of have, we have two sets of axes, right? These are the x's, and these are the y's, right? And we're optimizing two different energy functions, whatever they may be, right? And we've given a way to go from every point here to some point here and vice versa. Yeah? And now I'm saying if I do a line search here, well, I can take this vector and pre-multiply it by the matrix I used to go from x to y, right? Or rather invert. That gives me some direction here. What I'm saying is if I follow this guy to the minimum of this quadratic form, that's the same as following this vector to the minimum in his quadratic. In other words, these two optimizations kind of move in lockstep. Yeah? We're going to stick with the picture with this one instead of trying to do it algebraically. Maybe on your homework I'll decide on a few of these little lemmas that you guys can prove. But I think this is intuitive enough. Right? Basically all I did is I took my coordinate plane and I applied some linear transformation to make f less complicated, but linear things don't screw up lines. Yeah? So if I do line search over here, then I'm equivalently doing a line search over there. Yeah? Hopefully that's intuitive. Well, what does that mean? Well, first of all, let's define a vector v to just be this, the pre-image of your direction. So we're gonna talk about w's as being in this f bar space, right? And vectors v being in the s space, right? And the way that we go this direction is by multiplying by L transpose inverse, right? Because we multiply by L transpose to go this way. Yeah. So v is equal to L transpose inverse times w. Not a nice formula, but it is what it is. And in particular, let's say that these are orthogonal, right? This is the case we just argued about line search. Well, now we can plug in what that means for the v's, right? Remember that w is equal to L transpose times v. Yeah? Well, now this is a transpose of products. Well, same thing, product transpose, flip backward. Yeah? But look, this is LL transpose. We have a name for that. It's called A. Yeah? So, the two